So now in this video, we're going to look at using an NPN bipolar junction transistor as an emitter follower, or you could call it a common collector. Either one, same thing. The main premise of this is the voltage that you give to the base will be the voltage that you can output to a load, except for you lose that diode drop from base to emitter. So whatever voltage you give to the base, it's going to be about 0.6, 0.7 volts lower at the emitter down here. So I already have this wired up. This is a 2N3904. The left pin is the emitter, middle pin is the base, right pin is the collector. So if I swivel it like that, we have the pins in the same spot you see on the diagram there, from top to bottom. And so to demonstrate this, we will back up a little bit, and you can see this trim pot here. So I have 5 volts at the rail. We will grab this multimeter, and this trim pot is set about halfway, a little bit lower than halfway. So I'm guessing it's probably about maybe 2.4 volts. We're going to lose about 0.6 volts right there. So I expect at that point we'll probably have about 1.8 volts. And so we will quickly take those measurements. And that voltage drop base to emitter is basic transistor stuff that you learn. So there we go, 5 volts. That's mentioned a lot. 5 volts at the rail. The trim pot here though, there's a resistive element there. Depending on where you put the wiper, it makes a voltage divider. You can go from 0 volts to 5 volts, since we have a 5 volt power supply. And that voltage signal is coming to the base of the transistor. And in relationship to ground there, the base, the middle pin there, it's a little less than 2.4 volts, 2.355. So I expect about 1.755 approximately at the emitter. So, and there, it's pretty close right there. So we just subtracted 0.6 volts. Higher currents, the voltage may go up a little bit more. So what that means is that we can give that to a load. And fortunately I didn't put a ground jumper on. Actually, we don't need to. I can just take an LED. It's a little cramped here, but that happens sometimes. An LED there and a resistor. Put that to the negative rail, and you can see the LED is lit. Actually, you really can't see. We're not dealing with much voltage right now. So what we can do, since this is a voltage divider, we can just change it to whatever we want. So this is adjustable, and so I will turn it towards a more positive rail. Now you can see the LED lit up. But the main takeaway is that we are giving it a fraction of the voltage. We're not giving 5 volts to the base. Let's see what we're giving right now. And I'm shorting stuff out. There we go. We're giving it 4 volts right there. So the LED should be getting about 3.4 volts approximately. So I'll go to the top of the LED where the emitter is, and there you can see a spec below 3.4 volts, and the load can change. Now there's no load, we just have this resistor which helps hold the voltage at that point, and you can see the voltage is holding steady. So the load can change. It's just whatever voltage you apply to the base. Now let's look at actually I didn't need to yeah, let's go over here. That was with 5 volts. We can change the voltage that we are given the supply, and probably 12 is the max we should do, since I'm using a 1 kilo ohm resistor to protect the LED. So I got 12 volts, and current is limited. I was doing some testing. There we go. Let's go to 30 milliamps. That will be rough on an LED, 30 milliamps, but it won't burn it out, and it'll be a little rough on it. I think for a short period of time though, not terribly bad. So I didn't change anything here. Before we saw when we had 5 volts. In fact, let's make the math easier. Let's just go to 10 volts. So now we are at 10 volts. We got twice the voltage. We had 4 volts for a signal before, and we had about 3.4 7.4, I believe it was, volts at the output here. So we should have double that. We should have 8 volts for a signal, and then about 7 volts approximately at the output in relationship to ground. So I can go to the negative rail, we'll check the base there, and there you can see we have 8 volts there. At the rail we have 10 volts, and then at the output here we got a little more than 7 volts right there. So that was just quick math. And again, we can throw the LED on here. The LED is lit up now, and of course that should not change the signal to the base at all. Still 8 volts. And then we come to the top of the LED, which connects to the emitter, 7.37. So it just went down a spec, but it's basically holding steady right there. So that's the thing with the voltage divider, is as the power supply voltage changes, so does the voltage divider voltage. But if you have a steady voltage, or you don't mind those changes or whatever, you can see that the voltage divider works pretty well. The adjustable one, you can fine tune it, or you could use fixed resistors as a voltage divider. So this is a 1 kilo ohm resistor, put to the positive rail, and this one also a 1 kilo ohm resistor. So we will get half of the power supply voltage, and if that is your goal to always have half of the power supply voltage, but you got to remember we got minus 0.6 volts there. And then I'll do a jumper to the base. There you can see the LEDs on. So now we have 10 volts at the rail, and we should have, so 5 volts minus 0.6, about 4.4 volts at the emitter there. And there, it's not perfect, but that's really close. And again, you can change the load. The load doesn't matter as long as it can provide enough power. Right there. So the voltage stays the same. So now, that was with voltage dividers. Also, we could let's take the light-emitting diode. So now, this will have high resistance when it's darker, low resistance when it's lower, but these are only 1 kilo ohm resistors, so we got to keep it kind of bright to get below 1 kilo ohm. But what we can do is put it to the positive side of the voltage divider there, and under bright light the LED will light up pretty good, and then when it gets darker the LED will not light up. Pretty nice like that. And we can do the opposite. So we can make a light dependent voltage divider. So that's going to the positive rail now there, and then going there, so that goes to the negative rail. And now when it gets darker, the LED will get brighter, and when it gets bright enough, again, the resistor is kind of a low value for this circuit in particular, but you can see when I get my headlamp on there, the LED pretty much goes out right there. So there, we can make a light dependent version of this common collector emitter follower. So now right here I have what are called Zener diodes, and Zener diodes also need the resistor there. And so if you need a set voltage, that's when you can use the Zener diode. And I'm not sure which one this is right now, so let's see if we can get somewhat of a look. So one of them's 3.3 volts and the other one's 5 volts. So that says 5 right there. No, C, and then this might be the 3.3. So these are a little hard to read. You need a loop. But one of them says 5V1, but it'll be a little hard to read. So I can read that one easier. I think that's the 5V1. But in any case, you can't see the voltage on there. So it has a Zener voltage, and we put the cathode, the black stripe. If you hear a buzzing, it's Wednesday. They're doing the tornado siren testing, and so let's get that there. That's to the negative rail. So now it's either 5.1 or 3.3 volts. We can quickly test that. This meter is gonna start beeping if I don't get off of there quick. And so if you leave it on one setting for too long, it starts beeping. So let's take a look there. So that was the 5.1 volt Zener diode, and so we should have about 4.5 at the emitter where the LED is, and there you can see about 4.5, and so that's with 5 volts right there, or 10 volts I mean, with the power supply. So the power supply voltage has to be higher, but as long as it's higher by at least a volt or two, you got the right amount of resistance there, it's going to hold its voltage pretty steady. So let's push this quite a bit. Let's go up to 15 volts. Right there. And we should still be okay, but this is kind of high voltage for the value components that we are using. And now let's go, we'll see it's still probably 5.1, maybe slightly higher than it was before because there's more current going through the Zener, but the Zener holds pretty steadily its voltage even as current changes. So it lets through whatever current it needs to hold a voltage pretty well. And so we'll still have about 4.5 volts right there. So just a speck higher because more current's involved with the Zener, but it's holding steady. So this should be the 3.3 volt. Again, I'm having a hard time reading its values, but I could read the 5.1 easier, and sometimes I put them in the wrong bag when I'm done. So if I can't read the value is written on the bag, but it looks like the LED is dimmer. So I expect this to be 3.3 volts. Zener diodes come in a voltage. So this is a little higher, but we might have a little more current going through them, plus the lower value Zeners don't tend to be as accurate. But you can see it is pretty close to 3.3. And there we got 0.6 volts less. So it's not its rated value, it's the actual value it is giving the base. So about 3.6, then we lose about 0.6 due to the base to emitter drop right there. We got about 3 volts. So I showed the adjustable trim pot. You get a fraction of the power supply voltage. You do with the light dependent resistor as well, but the fraction that you get depends on how much light is falling on it and whether it's on the more positive or the more negative side of the voltage divider. The Zener diodes, and by the way, their Zener voltage is well reverse bias. So usually when you want a diode to conduct, you put the cathode to the negative side, the anode to the positive side. And it takes a small voltage, but once you reach like 0.7 volts, that's why we have that base to emitter voltage drop. But about 0.6, 0.7 volts, when most diodes are forward bias, they start conducting. The Zener diode will also conduct while forward bias at about 0.7 volts. I burnt out some though. I think they burn out pretty easy forward bias. But you put them in backwards, so any diode reverse bias, even the LED, will start conducting at some point if you raise the voltage enough. I did that with some LEDs though, and they were burnt out. They did not light up when I put current through them in reverse, and whenever I put any current through reverse, they stopped working after that permanently. I had to throw them away. But the rectifier, or the Zener diode, I mean, it is safe for it to conduct as long as you stay within its wattage rating while reverse bias. So it blocks up to a certain voltage, and then it starts letting current flow. And what that does, it makes a release valve. If the voltage goes up, it starts letting more current go through it, pulling the voltage down. And so it holds the voltage at its Zener voltage. Not perfectly, but pretty well. But this was mostly focused on the transistor as a common collector or emitter follower or a voltage follower, whatever you want to call it. Bunch of different names. Main takeaway is, other than the diode drop of the base to emitter that you lose, whatever voltage you apply at the input will be the voltage at the output. And again, this resistor, that 10 kilo ohm resistor, it does make it work better, but it's not always needed. So I don't have a whole lot to say about that one. I did have some circuits where I found I needed it, but like this circuit, I think will be perfectly fine without it. So we got 3 volts across there. If I pluck the resistor, the LED brightness didn't change at all, and we got pretty much the same voltage there. So I can't remember what scenario I really needed it. Probably if there's a lot of voltage being blocked at the output compared to what's being provided or whatnot, that might be when you really need it. But any case, it's better to have it there, but you might not need it. So I just used a 10 kilo ohm resistor there. So that's it. Hope you enjoyed the video. Thanks for watching. I will see you in the next video.